variable is 0. That basically we call the Laplacian. So because we are going to study the Laplace equation, so Laplace equation and then the solution of the Laplace equation will be a harmonic function. So that is our syllabus. Like oops. So that is our syllabus. We have to study about the properties of harmonic function, Poisson and Laplace equation. So there are a lot of properties of the harmonic function, and we are going to use this identity to prove those property. So this is basically your syllabus. That's why I just wanted to know what is the harmonic function. So let's come to the Green's first and second identity. This is not a part of your syllabus, but I'm telling you just in case if we need to use this identity, then we should be aware of that, because at this place we can see that we are going to use the boundary condition. We are going to use the boundary condition. So if we are in three-dimensional space, if the domain omega is contained in three-dimensional space, so delta omega will denote its boundary, and the boundary in three-dimensional space is nothing but surface. The boundary in three-dimensional space is nothing but the surface of that closed. If it is closed, then it represents the surface. Suppose this omega is a closed domain, then delta omega is going to be, that is basically the boundary. So it will denote the surface of that. Just visualize, like suppose this is it is not a sphere, it is not a cylinder. This is something a closed region in R3. This is something a closed region in R3. Then say this is omega. Then delta omega, that is basically the surface of this closed region. That is basically the surface of this closed region. So the boundary of this closed region is going to be surface of this region defined. So that is small details. We are going to use these details at every step. So you guys should be aware of these things. So Green's identity. Let omega be a bounded region enclosed by delta omega. What is the delta omega? If omega is a bounded region in R3, this omega is contained in R3. If omega is a bounded region in R3, then delta omega is going to its closed surface, because the region is bounded, the domain is bounded, so you can define its surface, and that will be the boundary of that closed region. That will be the boundary of this bounded region. So delta omega be a closed surface in the 3D space. Basically, to denote three-dimensional, we are going to use the coordinates x, y, and z. So 3D space, you can also call it x, y, z space. X-axis, y-axis, and z-axis. And let capital F is a vector. Capital F is a vector. I am calling it vector because we are in three-dimensional space. We are in a three-dimensional space. So you take any point F or any function, it will be depending on three variables x, y, and z. X, y, and z. So that's why it is called a vector, because we are in a three-dimensional. So the locus of this point, the locus of a point, if you choose any point, suppose P, the locus of this point is going to be x1, y1, z1. So that will form a vector. So the vector belonging to C1, and suppose that F is first order derivative is continuous. It means F belonging to C1. Then Gauss divergence theorem. Then Gauss divergence theorem. Have you noticed that this Gauss divergence theorem, we used to study the Gauss divergence theorem in our fourth semester of Licenciatura. But this is a very powerful theorem which we used at every level, like Gauss divergence theorem in engineering we used to study in the first semester, like engineering math 1, because formula is mechanical engineering. Yeah. So this Gauss divergence theorem plays a very vital role in all areas of mathematics, where we are going to talk about the volume and the surface. So omega is a bounded region. So it has a volume because it is in 3 dimension, and its surface, that will be the boundary of that omega, that will form a closed surface of the region omega. So the Gauss divergence theorem, delta omega f, and is any outward unique normal to the surface, and then omega divergence of f d of v. Say this question number first. Am I right? This is the Gauss divergence theorem. So dv is an element of volume and ds is an element of surface area, and n cap is the outward normal. Now Green's identity, which follows from the divergence theorem, are also useful and they can be derived. Suppose this capital F is F into phi, where F is a vector function of position and phi is a scalar function of position. I have expressed this in the form of f dot phi, f phi not dot. So what is the meaning of this thing? Just write out. I told you that this f is a vector. So for sure what is going to be vector, and if you want to visualize, so f will be like x1, comma y1, comma g1, and phi will be like some function x square plus y square plus sine g. So this is a scalar function, and this is a vector. So f is a vector function of position. If I choose any position in 3-dimensional space, so f is a vector function of position, and this is multiplied with a scalar function. So you can simply write it like x1 phi, comma y1 phi, comma z1 phi. This is also a way you can express it. There is nothing like that. Then integration over omega divergence of f phi dv is equals to n cap dot f phi ds. Now using the vector identity, gradient of f phi is equals to f dot gradient of phi plus phi gradient of f. So we have integration omega f dot delta phi. So we are using this and this. So f dot phi, and plus it is going to be phi delta dot f dv is equals to integration delta omega n f dot f phi ds. So I am simply passing this to the left hand side. dv is equals to minus integration omega phi grad dot f dv. Now, this is also an identity, but it is not named as identity. Since I told you that I am choosing this f as a position vector of, as a position vector. So here we can also take it its particular form. We can also take it its particular form. If this f is equals to gradient of psi, this is a vector of position, so this is also going to be vector. Then the equation becomes
This is the derivation of Laplace equation, right?
no. This
Okay.
also is writing the Green's identity because we are going to
Um,
use the Green's identity, and then we are going to study this Green's function as well. Like it is not the part of your syllabus, but we are going to study these things. We are going to use it on a broad level.
okay. There are like three identities, right?
Sorry.
There are like three identities, green identity.
Identity. You might be aware of the Greens has two identity. Like you can call it three identity. If you are treating it as a first identity, then the rest of the two are going to be like for second, third. But I'm not treating it as identity. So F is the end of psi and n gradient of psi into phi d of s. Now n dot gradient of psi. If you will calculate it in the unit word normal, then it is going to be del psi over del n, and this will be del 2 psi. So you will be getting the identity omega gradient of phi dot gradient. It really does not matter. This is the dot product. Uh, it does. Gradient of psi dot gradient of phi dv is equals to minus integration omega phi del 2 psi dv plus integration del omega. This is going to be del psi over del n. So phi del psi over del n, because since phi was a scalar and this is also going to be an scalar, so that's why we can write it in this form d of s. So this equation is Green's first identity. And one thing which is very important to notice here, either phi or psi, either phi or psi, both are second, like both are belonging to C2. So both are second, both are continuous, and its second order derivative is also continuous. Its second derivative is also continuous. So this is the most important thing which we need to keep in our mind, because we can see that this cannot be defined. This cannot be defined if it does not have a second order continuity. So that is the important thing. So it is just a pre-assumption. We are not mentioning here, but its second order derivative is continuous. If we interchange the role of phi and psi, and this is also known as Green's first identity. first identity. Suppose this is equation number 2 we obtained from 2. And then subtract equation 2 point, like equation 2 and equation 3. So this side will be cancelled out. So subtracting equation 2 to 3. This is the same, so it is going to be cancelled out. And we are left with integration omega phi del 2 psi minus psi del 2 psi dv is equals to del omega phi del psi over del n minus psi del phi over del n ds. Now you can see that this is the Green's identity and which we use a lot. This is known as Green's second identity. If you will be taking phi equals to psi,
And then, well, this is equal to 0, right?
no, I am talking about this. In this, if you are going to take phi equals to psi, we are deriving from the Green's first identity everything. If we set phi equals to psi, then gradient of phi square dv is equals to del omega phi del phi over del n ds minus. This is the special case of Green's identity. But the most important one is this equation number 4. This is the Green's second identity and the Green's first identity. These two are most important one. This is the special case. Let's do the derivation of the Laplace equation.
Well, actually, we strongly use like the Stokes theorem, right?
No, we are using only Gauss divergence theorem. I am not seeing this use of where we are using the Stokes theorem. I cannot see the Stokes.
Oh yeah.
Stokes theorem. I think this is a relation between line and surface integral. Something.
Yes.
Yeah. So we are not using the Stokes. We are using just Gauss divergence theorem. And since we are already aware of the Gauss divergence theorem, so that's we are using. Green's identity is very helpful in a lot of derivation, and we are going to, like when we will be proving the properties of some harmonic function, then we are going to use this Green's theorem. And then I am not going to tell you from where I am taking this identity. You just need to be aware if phi and psi is. So if again we recall that f is a harmonic function, then f is an harmonic function of n independent variable, then it's Laplacian. Although we don't know what is Laplacian, then its second order derivative, the sum of the second order derivative of the function f with respect to its coordinate is going to be equals to 0. So we can use Green's identity if we are taking f as an scalar function. So that is the thing which we are going to use when we are going to prove the property of the harmonic function, because f, its second order derivative is continuous. So simply we can use Green's identity. That is the use which we are going to do.
Can you repeat that?
Yeah, so I was saying that f is an harmonic function. F is a harmonic function. Suppose f is a function from Rn to R. Its coordinate that is coming from Rn and it is a scalar function, so it is going to R. So f will be a harmonic function if the summation of the second order derivative of f with respect to its coordinate is equals to 0. If the derivative, the second order, the summation of the second order derivative of f with respect to its coordinate is equals to 0. Later on, we are going to call it the Laplacian, but at this time, we don't know
Okay.
the summation of the Laplacian. So that's why I'm
Right.
saying that the summation
Mhm.
of its second order derivative with respect to its all coordinate is going to be 0, I varying from 1 to n. So f is going to be a harmonic function. It means its second order derivative is continuous. So we are going to use the Green's identity, because in the Green's identity that the function phi and psi should belongs to C2, and that is a property of an harmonic function. So it will be easier for us to use this identity. Now I would like to point out, even at some point a lot of students get confused with this symbol. This symbol, this is this is gradient, and when we put a dot and then a vector, then it works like a divergence. But if I am giving you only this operator, so what is the meaning of this operator? This is a Nebula operator, Nebula or gradient operator. If it applies on a scalar function, then it becomes a this scalar function this made this scalar function a vector function. And if we take dot product, then we take the product component wise. So always keep in your mind, because you guys are going to get confused between this symbol and this symbol. This symbol I am going to use for the Laplacian, I am going to give the definition, but this symbol is for Laplacian, and this symbol is very basic symbol which we are using since our beginning of the mathematicians. So this is a nebula symbol, gradient symbol. Just keep in your mind always. Even sometimes I am confused. Suppose this is a closed region, and this is a particle of mass m1 inside this region, say at point P, and there is a particle at point Q outside of this closed region, and it has mass m, and the distance between these two particles is radial distance, that is r, and this is center. So consider two particles of mass m and m1 situated at point Q and P, separated by a distance r as shown in figure. So according to Newton universal law of gravitation, the magnitude of the force F is going to proportional to m into m1, the product of their masses, and also m is going to be proportional to the square of the distance between them. So if we combine these two things, so m is going to be proportional to m over m1 over r square. And if we remove this proportionality constant, then a constant appear, and this g is known as gravitational constant. Why I am saying that this g is a gravitational constant? Because if I am saying that suppose this particle is on Earth and the other particle is on the moon. So if there is a force between these two particles, so these forces are basically because of the gravitation, its gravity and the gravity of the moon. So when we remove this proportionality, that proportionality constant is going to be the gravitational constant. It is somehow physics, but it is very easy to understand. If R represents the vector, R is equals to vector PQ, assuming unit mass at Q and unit mass at Q, that is m equals to 1 and z equals to 1. So the force at Q due to the mass at P. Now we know that I am taking this region as that is containing more than one particle. Basically I am choosing one particle and this is the particle. So this will try to attract this Q towards itself. Now if I am talking about the force at Q, so I am taking the force in the negative direction. So because of that, F will be minus 1 into m is 1 into m1 over r square, or we can write minus m1 vector r over rq, and this can be written as gradient of m1 r. Say it is your equation number 2, which is called the intensity of the gravitational force. Suppose a particle of unit mass moves under the attraction of a particle of mass m1 at p from infinite up to q. Suppose a particle of, here I am taking this particle at a distance r. Now I am saying that the particle start to move from the distance r and it moves towards the infinite. It moves towards the infinite. So suppose a particle of unit mass moves under the attraction. Why I am saying the attraction of the particle P? So I am assuming that this particle P is going to attract this Q towards itself. So that's why I am keeping, if I am going to calculate the force at Q, it means I am calculating the force in the negative direction, because here I am saying that P is attracting it, but the force at Q will be the negative of that force. To reach to the Q, we need the negative force. So suppose a particle of unit mass moves under the attraction of a particle of mass m1 at P from infinite up to Q. So just try to understand what is happening. A particle is coming from an infinite distance. A particle is coming from an infinite distance, and how it is coming? The particle at P is attracting that particle from the infinite, and then the attraction force is such that the gravitational force between those two particles is such that it is coming from the infinite and it stops here at point Q. How? The earth rotates in the orbit of sun and then it comes out. So this is basically this is the basically the thing. The sun starts like it is coming from the infinite and then reaches to the orbit of the sun. The earth starts from the infinite and then it reaches to the orbit of the sun and then it starts to rotate. So the same thing, a particle that is coming from the infinite, so P is attracting that particle from the infinite, and the attraction force between those two particles are in a such way that it stops at Q. It cannot come after Q because the gravitational force is in such a way. Like you can analyze in your mind how the Earth starts to come from the infinite and then it reaches to the orbit of the sun and then it starts to rotate to Q. Then the work done by the force Basically, the reason behind the derivation of this Laplace equation is that when you are going to use this Laplace equation, that is very important. It is very useful in the physics, in the earth dynamics. So the work done by a particle which is moving from infinite and coming to the point in R will be this. So this gradient, basically this is the derivative and it will be cancelled with the integration sign. This is defined as the potential V at Q due to a particle at P and is denoted by V is equals to minus m1 over r. Actually, I have written all the sentence in your notes, so that's why I'm not writing the sentence here. From equation 2, the intensity of the force at P will be, now if we use this V equals to minus m1 over r, so the intensity of the force at point P will be F is equals to minus gradient of V. So here we consider only one particle. Here we consider only one particle M1 in this region S. If we are considering there are n particles, suppose we are considering the system a system of n particles of masses M1, M2, Mn, which are at distances R1, R2, Rn respectively, then the force of attraction per unit mass at Q due to the system will be the summation of all the particles. So earlier F was the gradient of m1 over r. Now there are n particles of masses m1 to mn. So F is going to be summation of I varying from 1 to n gradient of mi over ri, and this gradient will come outside of the summation. So the work done by the force acting on the particle is and therefore del 2v is equals to minus del 2 summation I varying from 1 to n mi ri r is equals to summation I varying from 1 to n del 2 of mi over ri, and that will be 0 in the case when ri is not equals to 0. So this del 2 is nothing but we applied this gradient on the gradient of V. So it was already del over del x1, del over del x2 and del over del x3 because we are in 3D, and when we are applying it on del over del x1, del over del x2, del over del x3, so this is the dot product in between these two. So it is going to be del 2 over del x1 square del plus del 2 over del x2 square plus del 2 over del x3 square. So if we are choosing the coordinate x, y, z, so this del 2 will be del 2 over del x square plus del 2 over del y square and the del 2 over del g square. So del 2 v is equals to 0 is called the, why I am taking this 0, I will tell you there is a reason behind that. The Laplace equation, we also write it like del of v is equals to 0. So this is also represented by the symbol del. So this is the symbol of Laplacian. In the case of the continuous distribution, like suppose you are taking this S and it is taken in such a way that M1, M2, Mn, all the particles is distributed continuously. So in the case of, why this is taking 0? In the case of continuous distribution, of matter of density rho, we know that mass and density are related in a volume tau. So we have v of x y z is equals to tau rho xi eta zeta over r d tau. So this d tau will be basically dx dy dc, because tau is volume, so d tau is the volume product of the small element of the volume, so dx dy and dc. This represents the small element. Like I took this a small element, so this is going to be dx, this is going to be dy, and this is going to be dc. So the volume of this small cube in 3-dimensional will be dx dy dc. And if we take the integration in all the domain, then it will give us the volume of the whole domain. It will give us the volume of, we take a small volume, and since the distribution is in a continuous way, so we take a small volume and we take integration in the whole domain. So that will be the volume of the whole region. And this r will be, that is a distance of any particle which is situated at x, xi, eta, zeta. So the r will be x minus zeta square plus y minus zeta eta square plus z minus zeta square root of this. Now, and also assume that this q is outside of that. Now just employ these things, just use these values in this equation. Although it is done, I'm not going to do it, it is a long derivation. Just use this thing and then take the summation, you will be getting 0. So this was the Laplacian equation, del 2v of z is 0, or we call Laplacian of any function v is 0. Now if this solution of this Laplace equation exists, the solution of this Laplace equation exists for all the variable, so these derivatives are going to be continuous. These derivatives are going to be continuous. It means if the solution of this Laplacian equation exists, so that solution is known as the harmonic function. According to the definition of the harmonic function, what was the definition of the harmonic function? V, if phi is a function of n coordinates, suppose I am taking off only 3 coordinates, if phi is a function of 3 coordinates, then the second order derivative of this phi with respect to these 3 coordinates, del 2 phi over del x square, del 2 phi over del y square, and del 2 phi over del g square. So summation of the second order derivative of this phi equation is 0. So we call phi is a harmonic function. So if this phi is a solution of this Laplacian equation, then we call it a harmonic function. So every solution of the Laplacian equation which exists for all the, in all the domain, in all the spatial variable, will be called as a harmonic function. Is it clear that the solution of the Laplace equation is harmonic function?
Yeah.
Okay. Now I have given the derivative of the Poisson equation, and this is the similar. But the only thing is that we are assuming that there is a gravity field Here I was not taking the gravity field. Here I was taking only there is an attraction between these two particles. Here in the Poisson equation we take that there is a gravity field. So that will work as a source term. So if U is the unknown in omega that is contained in R3, then the Laplace equation del of U equals to 0 in omega, and it's non-conservative, it's non-homogeneous partner, and its non-homogeneous partner is F in omega is contained in RQ is known as Poisson equation. Again, I come to the point. This is the Laplacian. So just let me tell you a very physics thing. If suppose V is a potential, if V is a potential in magnetodynamics field where there is a magnetic field, there is an electric field. If V is a potential in the magnetodynamics or in the atmosphere, then the gradient of this V is known as electric field. This is the physics. So the gradient of potential is known as the electric field. So V, that is a scalar function. According to that, what will be the electric will be? Electric field will be a vector function, is not it? So this also plays a very important role. If we are discussing about the electric field, then we take the gradient of potential and that will work as an electric field, and in that case it will be del, suppose this is E, del E over, like you can say gradient of U, gradient of E is equals to F. So this becomes a first order partial differential equation with a non-homogeneous term. So the Euler-Poisson equation is a very important equation, and there is a lot of study about this system. I just relate it with every research problem so that if you are seeing somewhere that someone is talking about, if you are supposed attending some colloquium or something and you are reading this Euler-Poisson equation. So now you are aware of the Euler equation of gas dynamics. You are aware of that we have already studied in the unit 2, is not it? We are aware of the Euler equation. And when we take the gravitational field is there, when we take the effect of the gravity, that comes with the Poisson equation. So the combination of the Euler-Poisson equation, it means the study of the gases in the atmosphere where there is also some potential field, where there is some also a electric field. So this is a very emerging research topic in this area, these days, and a lot of author is studying about this thing. So if you read somewhere, so you can simply click how this equation is coming. Arise quite frequently in the physical science. These two equations arise quite frequently. I have already uploaded these notes. For example, solution of equation number 2 correspond to steady states for time evolution such as heat flow, wave motion, with here corresponding to the external driving force. I took the gravity field. In the derivation, I took the gravity field. And if we focus on this Laplacian equation, then if the solution exists and its second order derivative is continuous, in that case, the solution of this Laplace equation is going to be a harmonic function using the property of the definition of the harmonic function. We are not studying the property, just the definition of the harmonic function. So the solution of the Laplace equation are going to be harmonic function, but the solution of the Poisson equation is no more harmonic. So the study in the fluid velocity field and gravitational force. Like I am working on the ideal Poisson equation as well. So this is the area where I am using it. So this is also a research area. Now we come to the, because when we are going to study the solution of the Laplacian equation, the solution of Laplace equation and also Poisson equation, we need some kind of initial or some kind of boundary condition. We need some kind of initial or boundary condition. So if there is initial condition, it will be known as the initial value problem. If there are some boundary condition, then it will be known as the boundary value problem. We already have studied about the boundary value problem. So how many boundary value problems are there? I gave you the classification that there are three kinds of boundary value problems. Will you please tell me what are those kinds?
Dirichlet, Neumann.
Newman.
Don't remember the other.
Yeah, the third one is, I think it was Robinson. Even I don't remember, but it was Robinson. So there are three boundary value problem, but using the property of the harmonic function, as I told you, the solution of this Laplacian equation is going to be harmonic function. Here we have to use the Dirichlet boundary value problem. So there is a property of the harmonic function that it cannot vanish on the each side of the surface. So there is a property of the harmonic function. The harmonic function cannot vanish on the each side of the surface. So that's why we only use the Dirichlet boundary condition here. But in the research problem, we use a Newman Dirichlet boundary condition on a very broad level. So that's why people don't remember about the Robinson boundary condition. So to solve this Laplace and Poisson equation, and since this function u, when I was deriving the Laplace equation, what was the most important thing I took? What was the reason? Yes, I took a bounded region. The particle M1, M2, Mn were the inside of that bounded region. So if U is belonging in a bounded region, so it should also satisfy some certain boundary condition. That is basically the surface of that bounded region. So we see that now everything is the part of your syllabus. The condition which I am writing, everything is part of your syllabus. You should know. We see that the function u in a bounded region, omega in RQ should satisfy certain boundary conditions on the boundary del omega of this region in addition to satisfying the, okay, so if you are deriving the solution of the given partial differential equation, so to get a unique solution of this given Laplacian and Poisson equation, we need some extra condition. So if you say that this phi is a solution of the Laplace equation, then we need some extra condition to prove that this is the unique solution of the given Laplacian or Poisson equation. That is basically the basic need of getting a unique solution of the given partial differential equation to satisfy the Laplace and Poisson equations first and two. I did not mention, so it is first, it is two. So here our aim is to determine a second order continuous function psi which depends on x, y, z such that the Laplacian of psi is 0 within omega and psi is equals to f, some function f on the boundary of this omega where f is only continuous. We are not talking about the continuity of its first order derivative. F is belonging to C naught, it means f is continuous. We are not sure about its derivative because this is the boundary condition. Is called the boundary value problem of first kind or the Dirichlet problem. And since here I took a bounded region omega, here I took a bounded region omega, and I am defining this psi is defined inside of that omega, like within omega, and psi equals to f on the boundary f. So it is also known as, just you may mention as a remark, the above problem is also known as interior Dirichlet problem. Next, exterior Dirichlet problem. So, if this f is a continuous function, if f is a continuous function and is prescribed on the boundary del omega of a finite simply connected region, simply connected region omega, determining a function psi which satisfies Laplacian of psi equals to 0 outside omega and is such that psi is equals to f on the boundary of this omega is called an exterior Dirichlet problem. But most of the time we are going to work on the interior Dirichlet problem. This is the definition I am giving that you might be aware of this only. Next, we are going to solve the Laplace equation. Consider the Laplacian equation in only 2 dimension. Consider the problem in omega. Omega is contained in R2. So the Laplacian of u equals to 0. It means del 2u over del s square plus del 2u over del y square equals to 0. Or you can also say that this is the symbolical way to represent. For x, it is defined in a bounded domain. It is defined in a bounded domain, so that's why x is lying between 0 to pi and y is lying between 0 to pi. And since this equation is elliptic equation, this equation is elliptic equation, so you can also draw this thing.
We defined like the coefficients. A was the coefficient of the partial with respect to x, right? So in some, I don't remember.
This is the second order derivative of u with respect to x.
Yeah, but I'm remembering like you told us like the discriminant, like we can analyze the.
Yeah, you can analyze. So what is the characteristic of the second order PDE?
The characteristic?
Yeah, what is the characteristic of the PDE? Yesterday we studied the classification of the second order PDE. No? What is the classification of this PDE?
It would be B is 0, right? I know B is 1.
B is 0. B is the coefficient of uxy. No, not fully. It is B square minus 4AC. It is negative. We call it elliptic. Yeah, so this is going to be minus 4 cross 1 cross 2 minus 4. So it is negative. That's why it is that elliptic. Although I was just going to draw the things.
There was like a lot of terms. I don't remember like all of it. It's like a general quadratic.
It is yeah, elliptic. It is very easy to remember. Just pass all the derivative on a single side. Just pass all the derivative on the single side, and then you pick B A B C. There is nothing confusing. It is very easy. Just keep in your mind. How do you determine the discriminant of this? How do you determine the discriminant? Just if it is written like this, x square plus 4xy is equals to minus y square. So it is not that you're taking A from here and C from here. No, you pass all the square or all the terms on each one side and then you pick A, B, C. That is the basic rule. So x is varying from 0 to pi. Pi is 3.14. So 3, this is going to be pi. And this is going to be 0. This is pi is also varying from 0 to pi. So this is 0, 1, 2, 3. So this is going to be pi. So the reason, oops, I am very bad. I am very bad. I don't know how to draw. So this is the reason where the solution is defined. This is the reason where the equation is defined. Is not it? And now since this is a bounded region, oops, this is the reason where the equation is defined. Now this is the bounded region. Is not it? This is a bounded region. In this region, your equation is defined. Now we need some kind of boundary condition to capture the solution of the given partial differential equation. So say this is your equation number first. The boundary conditions are u 0 comma y is equals to 0. So x is 0, y is non-zero. On this it is u equals to 0. On this line u 0 comma y is varying but x is 0. So this is the line. The second is u pi y is 0. So on this boundary u is 0 for 0 less than y less than pi because x has been taken as a 0. Now u x comma 0 equals to 0 and u x comma pi equals to g of x for x lying between pi to 0. So when y is 0, this is 0, u equals to 0. But when y is pi, this is the boundary. On this boundary, u is g of x. Now you say that at this boundary u is 0. So when u reaches to 0, like at 0 comma pi, so what will be value of 0 comma pi? G of 0, and it should be 0 because this line is defined as u equals to 0. This line is defined as u equals to 0. So this is your boundary condition. Say it is your equation number 2 where small g is a continuous function, and if it is a continuous function, so because of the continuity of small z, u is defined 0 on x equals to 0, it had to satisfy the condition g of 0 equals to 0 from the left, and when you will reach here, so u is also 0 on this boundary, it means g of pi should also be 0 just because of the continuity of the function g. Because you can see that I took f belonging to c naught, so f is a continuous function. But because of the continuity of the z, this is a necessary condition that it should hold when the condition is given in this form. Now here we assume that u, the solution of the given PDE, u is can be written in the separated form as a function of x and a function of v. I am not going to solve it now today. We can continue it tomorrow. But this is your homework. If you can employ this thing at your place, so you just may continue assuming that the solution of the given PDE is written as the product of a function of x and the product of a function of y. So this thing which we will use here, and then we will take its variable separable form. So today we have covered the enough topic like the Green's identity. Please remember the Green's identity. Tomorrow we are going to study the properties of the harmonic function, and we also got to know the definition of the harmonic function. We study the derivation of the Laplace equation and how to define the boundary and what is the condition which it should hold. So we also got to it. So tomorrow we will start with this and we will study the solution of the Laplace solution of this problem, and then we will see the properties of harmonic function, and if time allows us, then we will also go through the Green's function. So this is not a very big unit. You will be able to finish it very soon, I think, because unit first and unit 2 took a very long time. It was a 16 lecture. Okay, so see you tomorrow. Bye.